I did, and we'll talk about that at the end of the class today. So every time you go through to solve, helpful to write down what you want. What are we looking for in this case? Moles of aluminum. It's going to become increasingly important to use your complete unit. The unit is not moles, it is moles of aluminum. You need that extra little piece there. We start with, and here's where I made the mistake last time, 3.42 times 10 to the 21st atoms of aluminum. Okay. If we now go through and look at our equation, are atoms of aluminum moles of aluminum? Well, no, so we have to do a conversion. Atoms of aluminum on the bottom, moles of aluminum on top. Do we have a conversion that allows me to convert the atoms of one unit to the moles of one unit?
Yes.
Yeah, that is effectively our dozen conversion. 1 mole of anything is equal to 6.022 times 10 to 23rd of whatever that is. In that case, we're using that conversion here. What number shows up in front of moles in our conversion? Okay, in our equal thing. So when we go through down to our conversion, the number that will show up in front of moles will be 1. The number that shows up in front of atoms? 6 point. Kind of rolls right off the tongue, doesn't it? Okay. If we go through and look at our units, what happens with our units? Atoms of aluminum cancel. Now all you got to do is plug it into the calculator. Okay. You do have to make sure you plug it into the calculator correctly, meaning that you're looking at your order of operation properly when punching it into the calculator. In this section, I would highly recommend that you use parentheses a lot. Okay? So whenever you're doing your calculation in the calculator, make sure you drop in lots and lots of parentheses, and that will help ensure that you do the order of operations properly. And the number we should end up with here is some relatively small fraction. Whole number. So we're looking at, what is that? 0.005? So roughly 0.005. Okay. Anybody care to know how I did that in my head? Okay. Well, if you don't care, that's fine with me. Okay. I am bad at math, but I can approximate pretty darn well. What's up?
This is kind of a silly question, but in the book, when we do the practice problems, and it says calculate the number of molecules in 0.0763 moles, you'd set it up the exact same way, right?
That'll be perfect for the next segue, because the very next question is effectively that question. Okay. So before we move into that, are there questions about what we've got up here? Everyone sees that relatively straightforward? Okay. You are using a more complex conversion factor, but that is it. It's the same thing that we did in Chapter 2. So when I told you to pick up the method in Chapter 2, as opposed to just saying shifting the decimal point, this is why. Okay? If you don't have a method at this point, you will get these questions wrong. Okay? So, back to your question, Melissa. What we're looking at, your question said how many chlorine atoms are in some mole of chlorine, right? Chlorine gas. So this is the same question as the textbook's presenting to you. So let's go through and break this one down. Same general idea. What do we want for an answer? In this case, it says oxygen atoms. Okay, our formula for oxygen atoms is O, not O2. O2 is the diatomic molecule, oxygen gas. This question does not say how many oxygen molecules. It says oxygen atoms. Our formula is just O. This is a very important distinction to make. What do we start with? 0.240 moles of oxygen. gas, O2. What was the question again? Oh, I'll adjust this question just to match that in just a second. Okay. So that's what we start with. It's what we want to end with. We need to do a conversion. Are moles of O2 equal to atoms of O2? No. So we have to do a conversion. What conversion do you want to try and do? Okay. Do we want to cancel out moles of O2, or do we want to bring in atoms of O? Because we can go either direction. I would argue moles of O2 is easier, but it's your call. Okay. Cancel moles of O2. So that means we'll erase our top one. We need to convert the moles of O2 into something. What do we want to convert it into? What's that? Okay, atoms. Atoms of what? Okay, I'm going to put atoms in quotes here. Atoms of O2. Are we allowed to do this conversion? This one is a valid conversion. The previous one, where it was atoms of O, is not valid. Why? It's a tricky concept. O2 is an orange. What is O? It's an apple. We're not comparing the same thing. Okay? It becomes really confusing in this case because the molecule we're looking at and the atom we're looking at, the difference between those names comes down to atoms and molecules. So it's a very confusing line to cross, but those are distinctly different things. Okay? One is a single atom all by itself. The other is a group of atoms. Those are different things. This conversion, where do I find that conversion factor? Okay. I gave it to you here. I can't remember if it's given to you on the exam or not. It's something you should memorize regardless. 1 mole is 6.022 times 10 to the 23rd atoms, okay, or units. 1 mole of atoms. So what number shows up in front of moles? 1. What number shows up in front of atoms? Okay. What's our current unit? Atoms of O2. Are those the same thing as atoms of O? No. Okay. So I have to do another conversion. The question is, what is that conversion? Why is the atoms of O2 not showing up? For every 1 molecule of O2, I have 2 atoms of oxygen. Mind blown. Where'd you get that information? The formula tells you. It says it's O2. What does that 2 mean? There are 2 oxygen atoms. You have the conversion factor directly given to you. You have to be able to do that interpretation. And I already screwed up the interpretation. What was our interpretation? 2 atoms of oxygen is 1 atom, again in quotes, of O2. What happens with our units? They cancel, and we'd end up with I don't want the number. Atoms of oxygen. Now all you got to do is put it into the calculator, and you can get your number of 2.890. Okay? Just because you happen to give me a number, and I still think I remember, 2.890. Right? Is that what you told me? Would this answer be correct? No. What's wrong with it? No. 2.890 oxygen atoms. I'm okay with that. Sig figs. How many sig figs did we start with? 3. How many sig figs in 2.890? 4, which means technically that's wrong. What would we have to do to fix it? Get rid of the 0. Now you're down to 3 sig figs, and you'd have the correct answer. Are sig figs going to come back and bite you here? Probably not. Okay, you might see one question where they show up, but it's not going to be explicitly tested on. Why? You to do 2 other conversions, I can get a multitude of wrong answers just by swapping those conversions around. Okay. Questions about this conversion as written? Okay. So my question, I said atoms of O2. Does that statement even make sense? No. An atom, by definition, is a single atom. Okay, so it shouldn't be written as atoms of O2. What should it be written as? It should be written as molecules. Oh my gosh, I'm going to write it out. Which you will almost always see me abbreviate as MLCS because I'm a horrible, lazy person. Okay? So any place we have that atoms in quotes, we can go back and change that to molecules of O2. Anybody have a problem with that substitution? I would make the argument you should. What is our conversion factor for a mole? Moles to atoms. What is the conversion factor I now have written in here? Moles to molecules. That's the argument that I would say you should be like, what's going on with that? Okay. 1 mole is defined as 6.022. 1 dozen is defined as 12. 12 eggs? Is that what a dozen is defined as? 12 eggs? 12 anything. 1 mole really just means, whoops, erased too much, 6.022 times 10 to the 23rd. So it's 1 mole of anything is 6.022 times 10 to the 23rd anything.
So you could do it with molecules too?
So when I go down to this conversion factor, 6.022 times 10 to the 23rd molecules of O2 is 1 mole. You'll notice in a quick second here on why I might abbreviate this, is 1 mole of molecules of O2. Those of you writing out units may be going, holy crap, I don't have to write that out every time. It's a good thing we start implying the molecules in our term. Okay? Questions on that? How would I change the question to make sure that you didn't have to use this conversion factor with the formula? Okay. Change the question, that conversion factor becomes irrelevant. What do I change in the question?
Just say O, not O2.
Oh, actually, pretty about, yeah, I can accept that. One of our changes could have been to make O2 just O. Now there's no need to use the conversion factor. Okay, I didn't even see that, so good catch. What's the other way we could have changed that question? Instead of saying oxygen atoms, say
How many atoms are in
oxygen molecules. The question that the textbook asked you was, how many chlorine molecules are in, I don't remember the number, 0.240 mole of chlorine? Okay. Well, that's right here. You don't need that extra little conversion using your formula. You're just using Avogadro's number. Okay? Questions? Those of you looking at this and seeing that this looks a lot of stuff. It is kind of a lot of stuff because what we are doing is taking Chapter 6, nomenclature rules and interpreting formulas, and Chapter 7, which is more interpreting formulas, okay, or not 7, yeah, chapter 7, and chapter 7 in just a little bit, looking at equations, interpreting equations, and balancing equations, and then combining all of that together with this concept of a mole. And if that was not enough, what do we also stack on top of it? Conversions into mass. Okay? So all of our standard conversions that we've already used in chapter 2. This is kind of the climax of general chemistry. Being able to put all of these conversion factors and convert all the way through. Anybody that tells you that general chemistry is anything other than conversion factors is wrong. That is what the entire class is converting from one thing to another.
Is that why you don't like teaching?
I find it incredibly boring. Okay? Because that is all it is. There is nothing else to it. You just convert from one number to the next. Okay? And you can go through and use formulas like crazy within it. That is absolutely a valid method behind this. However, if you follow the unit, there is no formula. Because everything you're doing is just trying to convert the unit from what you start with to what you end with. Everything in between is the formula that they tell you to memorize. You don't need to memorize a formula, just start converting units. Okay? What you need to memorize are conversion factors. Okay? Questions? Okay. 1 mole of a substance. This is kind of an interesting idea. If we take a look at all of these different mixtures here, those all represent a single mole of those individual substances. Does anything look kind of odd about that? They're all differing amounts or visual amounts, and they're all going to end up being different masses. But it's still a mole of a substance. Why can that possibly come up with a different mass? Each atom has a different mass. There is one of me and one Mahala. Do we have the same mass?
No.
No. She's probably very appreciative of that. Okay? Just because we have one of something doesn't mean it's the same mass. It's the same number of the substance. Okay? So you have to be a little bit careful when you go through and approach these things and realize where that impacts your relationships. When we look at this formula, I have 1 sodium and 1 chlorine. Do sodium and chlorine contribute equally to the mass of sodium chloride? No. Why? What is the mass of sodium? 23. Mass of chlorine? 35. Okay. That pairing will eventually get you to the total mass for that substance, but that doesn't mean just because there's one of each, they equally contribute to the overall mass. You have to take into consideration the mass of each of those individual components when you look at the overall picture. Our formula tells you the number of them. It does not tell you the mass. Go back to an equation. Let's actually see, does the next slide give me an equation? No, it doesn't. So let's pick an equation. Let's pick a random equation. Being the super creative person that I am, H2 plus O2 goes to H2O. If we really quickly balance that, we'd have 2H2 plus O2 goes to 2H2O. Does this equation tell me anything about the mass of hydrogen and the mass of oxygen needed to do this reaction?
No.
No, it only tells me the amount of each of those, the number of molecules of hydrogen. Which mass should be greater, hydrogen or oxygen?
Oxygen.
Why should the oxygen mass be greater to make this compound? There's more hydrogen. Oxygen is significantly heavier than hydrogen. We can derive and solve for those exact relationships using all of the mole stuff that we've been working with. Okay? So that if I gave you 5 grams of hydrogen, you should be able to tell me how many grams of oxygen you would also need to run the reaction. Okay? is kind of a reverse foreshadowing and a forward foreshadowing. You've done this already.
Sure.
Exam 1. You did it. In fact, I think we even use this relationship. Okay? And as the forward foreshadowing, you will be doing it again today. Okay? So one of the questions that kind of comes up is that you'll notice that chemists, or at least a lot of chemists, I happen to not be among them, really love a mole. Oh, it's mole day, it's mole this, it's mole that. Yeah, give me a break. When do we use Avogadro's number? When do we use a mole?
It's a really, really big number.
When it's a really, really, really tiny mass, so that I can convert my mass up appropriately, okay, and get it to a value that I can work with. After that, that's it. Well, how often do we go into the lab and use a really, really tiny mass? Never. Okay? So Avogadro's number, while incredibly important and useful, is pretty much meaningless to the everyday chemist. Because you will never work with that number. Because you will never work with a mass that is that tiny. Okay? Unless, heaven forbid, you become a physicist. Okay? A chemical physicist. Because then you got to work with it. Okay? Because that's what they're trying to do. They're trying to do things on that atomic scale. And some chemists get down to that level, but most do not. Okay? So the real kind of value and meaning behind this comes back to how we can use that number to convert the numbers of our atomic masses into a reasonable mass to work with. So what we end up doing is converting our atomic mass unit into a reasonable measurement, i.e. the gram per mole value. Okay? We walked through and did that conversion on whatever that last day was, Tuesday. Okay? Do we want to do another one just to see what's going on with it? Okay? I heard a sure. So let's go through and do it. Okay? I want to react carbon with something. Okay? So I want to measure out a reasonable mass of carbon. And that's going to become trickier to deal with. So I need to know how many molecules are going to be involved in that reaction. Well, if I look at the periodic table, what do we have for the mass of carbon? 12.01. And as we've talked about kind of so far this semester, the unit on 12.01 is AMUs. Okay. AMU is officially the mass per one, atom of carbon. Well, I can't measure the mass on one atom of carbon. I need a larger amount. Okay, I can't count that small. Okay, so I need a bigger number. So what I want to try and convert this into is a more appropriate number and a more appropriate mass that I can measure. AMU I can't measure. The balance doesn't do it. What unit do we use for mass? Grams. Okay? So what I want to go through and do is convert that unit into something else. I want to convert that unit of AMUs into what we use, grams. Where do I get that conversion factor? I know it's kind of grayed out on our screen. 1.661 times 10 to the negative 24th grams is 1 AMU. What number shows up in front of grams? Just to be annoying. Oh, way to cheat on that one. Good answer. 1.661 times 10 to the negative 24th. Officially, it's not the big one. It's the small one. The long one. And what number shows up in front of AMUs? 1. So cool. If we look at my units now, I have grams per atoms. So I can now go in and measure my grams, and I can relate that to atoms. Okay? That does involve a really, really tiny mass or a really, really large number of atoms. Because I can't measure something that small, I want to scale that number up to something that's in the range of my measuring abilities. Okay? So that's going to be using a very large number of molecules. that large number, Avogadro came through and said, this is the large number that I want to pick for this. So what we're now doing is converting the atoms of carbon into, say, a large number of them. Okay. That large number he decided to define as moles. Okay. And officially, it's not moles of carbon, it's moles of atoms of carbon. Okay. Same unit. That conversion, he said, well, I'm going to take a very large number of atoms, 6.022 times 10 to the 23rd atoms, and I want to define that as a mole of atoms of carbon. When we now go through to look at our units, what do we end up with? Grams per mole. Okay. So we now have a mass to a number of molecule relationship. Okay. So I'm in proper units and in units that I can measure appropriately, well, at least theoretically. That was the goal on this. Well, what number do we end up getting for that calculation? You get 12.01 grams. What did you get for the moles? What was that? 1. Why 1? When you go through and do that calculation, the number that shows up in the denominator had better not change the 12.01. If it changes it, then you don't have 12.01 anymore. So we have 12.01 grams per 1 mole. The number that Avogadro picked as the unit for moles, or that conversion, happens to be the exact relationship between grams and AMUs. Go figure. Okay? It's just the inverse of it. Okay? So that allows us to convert everything on the periodic table into now a measurable mass, and we can now use that to relate to the number of molecules within that mass. And if I know the number of molecules, I can then use my balanced equations, because my balanced equations can tell me how to relate the numbers of different species. Okay? So the lesson out of all of this, the mass provided on the periodic table should actually be in what units?
Grams per mole.
Grams per mole. That is what you will end up using. That's the lesson of Avogadro's number.
So we don't even need to do any of that.
You don't need to do any of that conversion. Okay? Because Avogadro's number will exactly cancel out your gram to AMU conversion. Okay? What is kind of fascinating behind this is, when did Avogadro come up with this number? A really long time ago. Before we even knew what protons, neutrons, and electrons were. No atomic understanding, and yet he's somehow able to not only comprehend this number, but come up with a way to relate that into measurable masses for each of our substances. Pretty incredible discovery.
Must have been an alien in a cave.
Yeah. Right. So this means when you look at the periodic table, you should be referring to it as the molar mass. Units on mass? Units on mass? Grams. Units on molar? Moles. It is the mass per mole. That is what your periodic table gives you, which coincidentally happens to be a conversion factor. That's all it is. Okay? So, I real quickly threw this slide up, I think, last Thursday. All we are looking at within Chapter 8 and Chapter 9 is conversion factors. Ultimately, all of the conversion factors are given to you in one form or another. Okay? You have to use some of your chemist knowledge to balance equations, balance formulas, predict products, to be able to get some of those conversion factors. Okay? But that information is something that you have access to. We can't tell you it's just a thing to memorize, because it's not a thing to memorize. It's potentially an infinite number of things to memorize. So don't sit there and try to be, oh, well, I'm going to memorize the molar mass for carbon. Well, what if I asked you for the molar mass of carbon dioxide? Okay. Yeah, you need the molar mass of carbon, but you'd also need to know the molar mass of oxygen. And why bother to memorize the molar mass for carbon? You have a periodic table which tells you the molar mass for carbon. Okay? So the trick to this is getting used to finding those conversion factors. Okay? So we started with conversion factors, individual measurements, converting grams to milligrams, okay? Converting liters to centimeters cubed. Okay? You did all that in Chapter 2. The metric conversions you're required to have memorized. We talked about the ones you need to have memorized. Which ones were they? Milli, centi, kilo. Okay? You need to know those. Other than that, your English conversion factors will be provided to you on the exam. I don't think I've found a single chemistry faculty here that insists that you memorize those. Okay? Are there other metric conversions that you might need to memorize? Yeah, that kind of depends on faculty to faculty. But millicenti, kilo covers most of your bases. The number of atoms can very quickly be found from a formula. The big issue with finding the number of atoms in a formula, you better make sure your formula is correct. Okay? So for instance, if I asked you for the number of atoms in iron 3 sulfate. Well, I didn't mean to write that. Let me try that again. Iron 3 sulfate. How many iron atoms are in iron 3 sulfate? Guarantee one of your answers is going to be 3, which is going to be wrong. Okay? It comes from your nomenclature. Your symbol for iron is Fe. Your symbol for sulfate, SO4. How did you know that? You memorized those because I told you to memorize those. If you didn't memorize those, yeah, you're now going to be in problems. Okay? What is the charge on iron? +3. Okay? Notice that where I'm writing the +3, I'm not writing it to the upper right-hand corner. Why? It's not that it doesn't matter. What's that? It's not the charge on the molecule. If I start writing iron +3 in the upper right-hand corner, that makes it look like I have iron and sulfate separated from each other. They are not separated from each other. They are together. They are in a compound. Okay? So I'm trying to put that charge in a way that I know it's associated with iron, but it's not part of the formula. So I put it directly above it. Could you put it anywhere else? Yeah, you can put it directly below it. Okay? You could even write it upside down. I don't care. Okay? But try to avoid writing it in the upper right-hand corner. What is the charge on sulfate? -2. Okay? Would this formula be balanced? No. So what we would officially have to do, depending on the method that you want to use, that has to equal 0, because to come up with a compound, our overall charge must be 0. The X happens to be the number of irons. The Y happens to be the number of sulfates. Okay? So for those of you that panic and say, well, I don't want to deal with that formula because it's never going to show up again. Sorry. Not really, but sort of sorry. Oh, and I recorded that. That's always good. How do we decide what X and Y are? Guess. Say X is 1. Would it work? No. So your guess was wrong. So what do? Guess again. X is 2. Oh, look at that. It ends up working.
It does work.
X is 2. Y ends up being 3. Oh, why is that wrong? I need to make sure that that is not SO43. It is SO4, 3 of them. Use the parentheses. So back to the original question, how many irons are in iron 3 sulfate? 2. At least 2 people did that in their head already. That's because they've been doing the practice and they can do it in their head. If you can't do it in your head yet, you need more practice. It's fine. Keep doing practice until you can get it in your head. Okay? So the number of atoms can come out of your formulas, and your formula must be balanced. This is a confusion when balancing equations. When I ask you to predict a product, your product must be correct. The product must be balanced. Okay? You have to make sure your charges balance within your individual products. Once your product is balanced, then, and only then, can you move on to balancing the equation. From the equation, we have an extra piece of information here. I now have the ability to relate any atom to any other atom or molecule within my equation. If I give you one tin molecule, or tin ion, sorry, tin plus 2, how many iron 3s do we need to react? 2. Why do we know that? It's what the balanced equation tells you. For every 1 tin, 2 iron plus 3s need to react. Okay? If I give you 43, that's a bad number. You won't be able to do that math easily. If I give you 20 tin ions, how many iron ions do you need? 40. You're just using a conversion factor that you're pulling out of the equation. If I give you 40 tin ions, how many mercury ions do you need? Mercury in the equation? No. So do you have any idea how to answer that question? No. Fair game. You don't know. So look for that answer that says you don't know. Okay? The next big one is your number of moles. Okay? Moles can come from a variety of places. You can get it from atoms and molecules. Okay? Because mole is just a counting of them. We can also get it from our formulas and our molecules. If I give you 1 mole of iron sulfate, how many moles of iron are there? Two. Mind-boggling. How'd that happen? What is a mole?
It's just a
Really large number of something. Okay. A mole of apples to a mole of oranges. Is it the same number?
Yeah.
All it is a number. A dozen eggs is the same number of eggs as a dozen oranges is a dozen oranges. Okay. It's just a number. So if I look at the formula of iron sulfate, if I gave you 2 iron sulfate molecules, how many irons are there? 4. What if I give you 6.022 times 10 to the 23rd? I know that one's a bit mean. Iron sulfate molecules.
yeah, exactly.
12.022 times 2.
12.044.
That's what the balanced formula gives you. It tells you the number relationship. What is a mole? A really large number, but it's consistent between your substances. All you're using is the conversion factor out of your formulas. Okay? The last big one, your atomic or your molar mass, comes from your periodic table. Okay, whoops, that should not say grams per atom. That should say what unit? AMU per atom, or grams per mole. At this stage in the game, you might be expected to use AMUs per atom. Okay? So kind of be aware of that. As you move further through, you're going to be shifting to grams per mole, because that is a measurement that we can actually measure and use. Yes? No, I do not expect you to memorize the 1.661 times 10 to the negative 24th grams was 1 mole. I do not expect you to memorize that. Right? That said, you probably already have. 6.022 times 10 to the 23rd. Remember we said was the inverse relationship? What is 1 divided by 6.022 times 10 to the 23rd? 1.661 times 10 to the negative 24th. Okay. You should memorize Avogadro's number. The AMU to gram conversion you do not need to memorize. I will give you that for sure. Okay. Questions? When you're looking at your problems, you will always have two pieces: the measurement, the number, and a substance, which is going to include the unit and whatever it is. Okay? So if I have 12 eggs, that is 1 dozen eggs. You have to include the full unit. Okay? So your conversion factors can be found in a variety of places. Most of them are going to be found on the exam or coming from your brain. Okay? The next big part is how do we go through and do these conversions. You'll notice that I've got this organized as a nice straight line. We can go from atoms of one molecule to atoms of a different molecule. The only way I can do that conversion is by pretty much going through our line. Okay? So if I give you atoms of X, to get to atoms of Y, you need to be able to skip through these conversions. The most important conversion for all of this, the mole. When in doubt, convert your unit, whatever the unit is, to moles. Because from moles, you can go out to anything, including moles of another substance. How do we get to the other substance? Through a balanced equation. All right? So what I try to include in this line is where you would find those conversion factors or what they are and allow you to get through it. Okay? Takes practice and just working through. Okay? You don't have to go through each and every single step. Sometimes you can skip steps depending on what you're working with. You will notice that there are a variety of other ways to go through and organize all of these possible conversion factors. Okay? Ultimately, I don't think it's that big of a deal because if you start saying, well, this is the way it's organized, you're memorizing a formula, not the units. The units get you to the answer. Okay? Another way you could look at this is really useful for the people watching at home. If we look to the board on my right, your left, we have this lovely big drawing of how you can convert between moles to anything else. Okay? That's fantastic. Okay? That's beautiful. Tutoring Center put that together. They've done a really good job of organizing that and kind of putting it all in one place so that you can see how you can convert out to all these variety of species. I would argue it is a crutch. If you end up using it too much, all you're going to end up doing is relying on that, and then you're going to get confused further on down the road. Use your units, track your units, follow your conversion factors. Right? All you need is this class. Feel free to crutch away. I'm cool with that. Okay. Questions? Okay, so this looks familiar, right? For every 1 mole of oxygen gas or oxygen consumed, 2 moles of water are produced, 9 grams. All of those conversion factors are given to you. This is the equivalent of that question, which we're going to make a quiz. But in this equivalent, so when you look at this question, you are responsible for being able to do every single aspect of this. And at this point, you have the full ability to do it. You may not believe it, but I do. Right? And I have every confidence that you can figure this out. Okay? First thing, Chapter 7. What did we do in Chapter 7? We looked at reactions. Is a reaction happening here? So what might be a useful thing to include? A reaction. Okay? If you don't draw a reaction, you're going to have a really bad time. Okay? So let's start with the reaction. What information are we given that would say, oh, I'm doing a reaction? oxygen gas, which we need to know is O2 because oxygen is a diatomic element, is reacted with hydrogen gas. What is produced? What is phenomenal about this equation? I now have the ability to relate oxygen to hydrogen, or oxygen to water. You know how to do this. Don't get bogged down in all the excess information. Okay? You have to start whittling things out and pulling things out and looking at them. Okay? Before we can find the relationship between oxygen and water, before we can use this equation, what do we have to ensure? It's balanced. If it's not balanced, we're doing a completely load of crap amount of work for nothing. Okay? Is it balanced?
Yes.
No. What do you need to balance it? 2 in front of the hydrogen and 2 in front of the water. Now the equation is balanced. Now I have a relationship here. Okay. What am I given? 9 grams of oxygen. What am I told about the hydrogen? Excess. What does excess mean? More than enough to do whatever I want to do. Okay? So I don't even need to worry about the hydrogen. What am I trying to solve for? Water. Good call. Let's make it a little bit more detailed. It's not just a question mark, but it's a grams of water. So my answer needs to be grams of water. What do I need to start with? 9 grams of oxygen gas. Okay. If we look at our equation, I'm starting with grams of oxygen and I'm ending with grams of water. I notice a lot of people are trying to cancel oxygen so they have grams. You can't do that.
Nope.
Your unit is grams of oxygen. The unit is not grams. The unit is grams of oxygen. You can't cancel oxygen out of the unit.
I was afraid.
Okay? The next big tricky thing here. We're starting with oxygen, we're ending with water. Which means we are changing the substance. Okay? If I give you a tire, what can I change that substance to? I can change it to a car. How do I change it to a car?
Add the rest of the car.
Add the rest of the car. Or I could change it to bicycle. How do you know what I'm changing it to? You don't until you look at the equation and say, what am I trying to convert to? You need a balanced equation to do the conversion. That's why it's there. That's why we spent so much time looking at equations. It gives us that information. Okay? To do that conversion, if I give you that tire and I want to convert it into a bike, I want to do a car. You're all used to cars. Okay? I give you that tire and I give you 400 grams of tire. How many cars can you make? Okay, let me try again. That was a little bit weird. Instead of giving you 400 grams of tires, I give you 4 tires. 1 car. How'd you do that? What does the equation tell you? To build a car, you need 4 tires. Does it tell you anything about the mass? I give you 500 kilograms of tires. How many cars can you make? I don't know. How big is a tire? Okay. You don't have that information. The equation tells you the number of them. So when I give you the mass of oxygen, I'm setting you up with, well, I don't know. What should you convert the mass of oxygen to? The number of oxygens. How do we look at the number of oxygens? Okay. Moles is a very valid answer. It's probably the easiest answer. You could also convert it to atoms. Okay. That is a crappy pathway to go, but it works. Why is it crappy? 9 grams of oxygen is going to be a stupidly large amount of atoms. You're working with powers of 10. How many of you liked dealing with powers of 10? Okay, how many of you did not like working with powers of 10? Okay, at least get some response there. Right? Which means instead of converting to atoms, I should convert to moles. What did I tell you right before this question started? When in doubt, convert to moles. How many people converted to moles right away? Yeah, that's probably something you should be doing immediately. Everybody's hand should be going up. Right? So let's convert to moles. Grams of oxygen on the bottom, moles of oxygen on top. How did I know grams of oxygen should have been on the bottom? I don't want that unit in my answer. It needs to cancel. What is the relationship between grams and moles for oxygen? Where do I find that conversion factor? Periodic table. I would argue it's not just the periodic table, because the periodic table tells you the grams of oxygen per mole of oxygen is 16. This is not the grams of oxygen. This is the grams of oxygen gas. I have to determine the molar mass, whoa, that was a weird line, of oxygen. The molar mass, or mm, for our oxygen molecule will be 16, because that is the gram per mole of a single atom, times 2. Okay. Where does the 32 show up? Careful. In front of grams. That's where the 32 shows up. The 32 will then show up in front of grams, which happens to be on the bottom. What number shows up in front of moles? 1. I now have a number of oxygen molecules. Can I convert the number of a species to the number of another species? How? So I want to get rid of moles of oxygen. Ideally, what do I want? Ideally, I'd want grams of water, but there is no relationship that shows between the substances' different units. So I can convert it to moles of H2. Yeah, I can convert it to moles of H2. Does that get me closer to my answer? What do I want for my answer? H2O. So does converting to moles of H2 help me? It's not wrong. I can still use this. But ultimately, what do I want to get to? H2O. So instead of going to H2, let's whole hog it. Let's go straight on to H2O. Where do I find this conversion factor? The number of oxygens to the number of waters. From the balanced equation. What number shows up in front of moles of oxygen? 1. How do you know that? What number shows up in front of the moles of oxygen in our balanced equation? 1. Okay. We have to be careful. Sometimes nothing means 0, sometimes it means 1. If it was 0 in this case, we wouldn't have written oxygen. What number shows up in front of the moles of water? How do you know that? That's the number that shows up in front of water. Okay. You now have moles of water. Is that the answer? No. What do we want as an answer? And we want grams of H2O. Can I relate the mass of a substance to the mole of a substance? How do I figure out that information? The same way I did as oxygen. What do I do? Figure out the molar mass from the periodic table. What is the mass of hydrogen? 008. Oh my gosh. Does it really say that? Okay, good. It's like, I don't want to write that. Okay. There's 2 of them. So I have to multiply by 2 plus 16 because that's the mass of oxygen. And I get a mass of being 18.02 grams per mole. What number shows up in front of grams? 18.02. What number shows up in front of moles? 1. Track your units. Grams of oxygen cancels. Moles of oxygen cancel. Moles of water cancel. What unit do we have? Grams of water. Okay. What's fun about this is you just went through and did 3 conversions. What I will go through and do on this answer is write out this work so I can see everything, and then I will go through and instead of dividing by 32, I will multiply by 32. Wrong answer number 1. I will go through and instead of multiplying by 2, I'll divide by 2. Wrong answer number 2. Get the idea? Okay. You have to understand how to solve the problem. This problem is something that is a show your work. Multiple conversions, multiple equations, multiple balancing. This is the cumulative effect of everything we have done this semester. Okay. You have done each and every single one of these steps multiple times, okay, throughout the semester. It is now coming together all as one big piece. If you have a weakness at any one of these points, guess what happens to your answer? It's wrong, and it disappears. Okay? You have to run it all together, slow it down, look at each and every single step. If we go back to this deal, I gave you grams of A. How do you convert to moles of A? Periodic table. Huh, look at that, I told you that. Moles of A to moles of B. How do we do that? Oh, look at that. We did that too. Moles of A are moles of B to grams of B. Oh, shoot, I didn't tell you that, except it's a repeat on the other side. Okay? It is not just multiplying your numbers through. You have to follow the units and organize them according to the proper fashion to get you through and solve a problem. Yes?
So when you went out and did that, it gave you like 10.1.
Oh, I have no idea what it gave you. And I just deleted all my work. So what do we do? 9 divided by 32. So 0.33 times 2, 0.66 times 18. I can't do that one. That's going to be close to 10, yeah, because it's a little bit more than half, so it should be about 10. We already took that into account in our equation. Yep. So right in the middle of the equation where we converted from moles of oxygen to moles of water, we did the 2. It's already there. The answer is 10 something. So, interesting point. On the exam, you'll notice the exam gave a different answer. Why? That very first line, for every 1 mole of oxygen consumed, 2 moles of water are produced. 16 grams of oxygen equals 1 mole of oxygen. Is that true? No, it's 32 grams of oxygen is 1 mole of oxygen. Okay. That's a pretty big typo. Okay. The reason why I actually made that typo, now that I look at it, if I had written 32 grams of oxygen, somebody's going to look at the periodic table and say, no, oxygen is 16, not 32, and you're going to flip out at me. So because we hadn't had the concept of what an oxygen gas molecule was because of diatomic characteristics, I had to leave it as the 16. So that's why the answer on the exam came out differently. When it came to the exam, if somebody had already had the background experience to know those conversions, I accepted credit for that too. Okay. So what we've done is every other little step within this. What I expect you to go through and do when it comes to the exam is to convert. Give me a molar mass for any formula. Okay. What's fun about that one? It's a hell of a lot easier than that last question. Okay. You are expected to do each of the individual pieces of that conversion. I wish I had that equation up there. Each individual step you are responsible for. The big kit caboodle that we see here, I will make that extra credit. Okay? You are responsible for each of the smaller steps within it. Okay? On Tuesday, I know we're running out of time. We'll do some more conversions, getting you practice with the individual steps. So there's a bunch of practice there. We've got the equation concept showing up. So that goes back to the same thing we just looked at. We will probably make it all the way through to...
I don't know. Do you want these or do you?
that slide.
You want these or not?
This means, yes, I do want... Oh, man, I meant to collect that before we talked about the answers. Damn it.
Yes, I wrote it down.
This means when it comes to the exam, okay, the exam is officially, I believe, next Thursday. It is not going to cover all of Chapter 8 and Chapter 9. Okay. Limiting reactant concept, percent yield, not on the exam. Empirical formulas, molecular formulas, okay, which are talked about in Chapter 8 in a little bit more detail, not on the exam. Those 4 topics won't show up on the exam.
Which four?
Everything else you need to work with.
Which 4?
I will post an announcement to Canvas about those, so those people that weren't here can actually get access to that information.